Okay, the first lightning talk is from Alex Rasher, again from NOAA. So, do you know how to present in preview? I think it'll work. Or we can just do it like this. Let's see. There. All right. There. Up and down should work.
All right, I'm just going to rattle off a few quick feature requests, and feel free to jump in at any time if anything's especially interesting or uninteresting. Okay, I'll have to work myself up to it, so I get warmed up. All right, I'll start off with an easy one. It would be cool to allow any package in the LMOD hierarchy. Right now, it only allows you to include virtual packages. I don't think there's any deep reason for that. This isn't a critical one, because... Sorry?
I'm pretty sure that's fixed already.
Is it?
That's how fast we are.
Okay, hold on. Am I safe to open this link? No, no.
I will triple check that it went in and I'm not just missing it in my list of open things.
All right, cool beans. Okay, next thing is it would be cool so we do, especially in our CI, we do a bunch of SPAC install double dash test, and right now we basically have to go in to look at, install time test log.txt or whatever to make sure that that things actually ran. So if it could actually show that tests are being run, and better yet, if it could show 15 out of 15 tests being passed or something like that, that would be pretty cool. Awesome. Okay, maybe this will get a little more involved here. So we define everything through CMake and CTest in our packages. It would be nice to be able to customize our test behavior, preferably in a way that doesn't affect the hash. In practice, it's not really a big deal because we end up building things on each HPC anyway. So if we have to customize it that way, that's fine. But right now, we basically just end up maintaining some logic in our packages to say, oh, I don't want to run this package with this, or maybe I have to add a special variant to say, I only want to run this set of CTest tests or whatever. Like I don't want to run the ones with MPI on this system or whatever. So there's a few possible solutions I can think of. I guess for context here, when I brought this up maybe like a year or two ago, I think the response was basically to use environment variables, which feels a little ugly and potentially redundant, and also probably hard to sell for, especially for third-party developers who have already implemented these things through CTest. I think that would involve basically going into the CMake CTest configuration and implementing a bunch of variables to then dictate the behavior. But it seems like it should be pretty straightforward in principle to integrate this. So a more specific solution could be something like CMake args or test args variants. At least the test args one could be ideally something that doesn't impact the hash, but again, not really a big deal for our use case. More broadly, something like test-only variants, which would basically just be variants that aren't used to calculate the hash, and then like a really general solution would be some mechanism for package.pys to read from packages.yaml, where the user could just, or a developer could just kind of populate their, populate some extra attributes or something like that that can just get arbitrarily used in some way in the package.py. I prefer the first one, or one of the first two. Sure, yeah, that'd be great. Okay, so this is maybe my most out there one, is especially for the packages that we deploy but don't maintain. It's not too uncommon for us to just run into little issues with, especially the developers we work with on other teams have gotten better about, maintaining SPAC packages and this sort of thing, but it's still not perfect. So it would be kind of cool if for our third-party libraries, when the developers are going to make a package.py update in main SPAC or in the main SPAC packages now, having some infrastructure in place where we can just run a run unit tests for basically just provide a spec. I don't know if this would fit within the SpacBot framework, but at least what I notionally have in mind would be something like @SpacBot test package, and then just give it a spec. I think this would work nicely, especially in this case. Maple would be like a package that has MPI tests, but that we probably wouldn't want to bother running in a 1 or 2 CPU runner. So having that test args there to just run the non-MPI tests or something like that would additionally be cool. So yeah, again, I don't know what's kind of practical here from an infrastructure perspective, but especially for the third-party libraries that we deploy, it would be cool to have an easy way to check changes to SPAC packages. Okay, I don't hear any yelling or grumbling, so that's fine. Thank you. And then the last thing I have is I put in a PR for this a few weeks back. As I mentioned in my talk, in the operations context, we're constrained to only install from a certain set of packages. So basically, we'll just have a text file that we want to be able to tell SPAC, only consider these packages for concretization. So the way I'm implementing it now, or would like to implement it, is to just be able to set packages all buildable false to provide kind of a default, and then we can just selectively decide which packages we want to incorporate. That I think would be good enough, and then I'll just have my own kind of scripting or whatever that takes care of actually doing those configurations based on a text file. That felt like the most straightforward or sort of SPAC-ish way to do it, but it's the sort of thing that if other groups had similar interests, then it might be worth talking about other ways this could be implemented, like pointing the SPAC configuration to a text file that has a list of allowed or disallowed packages or something like that. So for this one, it's really just more a matter of getting a sense of whether there's anybody else with a similar use case. If not, I'm happy to just kind of push ahead with what I have, but yeah. Greg?
That's supposed to be working already, so it's a bug if it's not.
Okay, yeah, I had a feeling it might be, so yeah, fair enough. Because, I think when I tested it like a year ago, it seemed to work fine, and then more recently, just didn't seem to have that behavior. So, okay, sounds good. All right.
You want to go next? Yeah. All right. If I can find it. Oh, here it is. Yeah. Okay. So the next up is Mattia Mancini. And I guess we'll do slideshow and go for it.
Thank you very much. Hello. So today I will show you a bit, speak a bit about our project and how we use PAC. So we are the square kilometer array. What it is 2 telescopes. So one low frequency, 50 to 350 megahertz, and another one with higher frequency, 350, 15.4 gigahertz. But we are also an intergovernmental organization that is spread around the world. Many countries are contributing to it. And it's not just a telescope, but it's also something more I will tell you later. So how does it work? No, not that. Nothing dangerous yet. How does it work? How does it work? Basically, it's an interferometer, so we record the raw voltages from the antenna, then we use a correlator to combine the signals so that we can point the telescope in the sky. Then we have an online calibration, and then an offline batch reduction that finally creates an image. And this is one of the first images for the SKA law. So, but talking about data, it's a lot. So for the low station, we have 2 petabytes per second when we record directly from the antenna, and we have to reduce it down through combination through beamformers, like what I showed you before. And then there is a central signal processor, which is the correlator, and then we have the batch processing, which does the calibration and the imaging. And then at the end, we ship it to the regional centers that are distributed all around the world and provide the computation power for users. And this is all terabit per second, but an observation lasts several hours, so I'll let you do the math to understand how much data it is. So right now, I'm working on the batch processing side, and we use a AWS staging cluster, and soon we will have a production cluster. We do the software deployment through GitLab and Spark to distribute also our software. And we use it as job scheduling Slurm and Dask. So our Spark setup is basically we have Python and C++ software built through CMake most of the time, luckily. And then we have packages for Spark for these recipes. And then we have 28 target packages that become 555 when we concretize everything. And all our target packages are smoke tested. And we currently overwrite 33 of the Spark packages upstream because either the version is too old or some patching is needed. But we all do this not just for us. We also do it to support the Radioastronomy community to use our software through spec recipes and soon through container images that they can just download and use to run again the analysis or to reduce their own data. Common issue that we encounter, a bit like a lot of people mentioned them already, is we spend several hours in concretization and building. The build cache helps a lot, of course. Some packages were linked to the wrong library, and we realized that once we deployed on the cluster, so it was a bit too late, but luckily we now introduce mock tests after the build, so that we can catch the errors early on and not release those one before we patch it. And then finally, migrating to version 1.0 took some effort, so please don't migrate anymore. Make it easier. Don't let us migrate anymore. So anyway, in our Spark repositories here, we are open to suggestion for improving our setup. You can scan the QR code, or you can just go to the URL. And that was it. Any question? Oh, sorry.
Here somewhere. Yeah, maybe. I stole it for myself.
Yeah, so can you talk a little bit more about the package, the 33 package override? So, because if it's versions, you could work off the built-in and update them unless you have some strict version requirements or overlay. Like
yeah. So for instance, we have some of the library use a newer version of Dask, and that was not in the upstream, so we had to have our own recipe.
Oh, okay. Yeah, but it doesn't take that much to change it and then do a PR. Like,
That's what we are planning to do. So we had a bug fix, but it took like a while to have it merged, and we need to move very fast because we have other problems as well to solve. So that's why we override it. But yeah, it would be nice.
Okay. I was just trying to understand the use case because sometimes you have to like pin to a repository version and then have a overlay, and I didn't know if that was the situation, but it sounds like it was not.
Yeah, we try to have a fast turnover because we are currently in the development and the building of this telescope.
So this use case where they have a separate repository is one that I've encountered a few times, and it ties back to oftentimes requirements from customers that they pin to a version that's one less than the latest, and it has to be a release. It can't be developed. It can't be anything that could change. So that forces them to take all the deltas into their private repository and then flag them differently.
All right, let's thank our speaker one more time. All right, Patrick is next. Thank you. Yeah, sure. Whoa.
Careful. So hi, I'm Patrick Gartung from Fermi National Accelerator Laboratory, not the lab that makes Fermis. Our group is in charge of software that's common to all the experiments, all the neutrino experiments in particular, at Fermilab. And we have a couple suites of software. Just to read them off is Larsoft, Newsoft, the ART framework and 5 data management utilities. And currently, we have 3 experiments that are getting on board with our SPAC builds. It's the Dune experiment, SBND, and Icarus. So each of the experiments has software that's built on top of this stack. Plus, they have their favorite analysis tools, and it's usually a Python package or something, and that can be a problem sometimes, but I'll talk about it. So we are trying to create granular environment configs so that we maintain our part and they maintain their part. So each of the experiments and software projects have their own SPAC packages repo for things that are very, very specific to us. And we also have them provide a set of root specs that need to be built and a set of package requirements. And so here, these are the ones that are in our control, and I'll move on from there. So the config files, we make use of config variables, including the handy tool chains, and we also pull in files to figure out what the root specs are for an environment. We have a set of scripts that were developed for setting up and configuring a SPAC installation the Fermilab way, and it's the Fermi SPAC tools, and it also has in there our config files, like things that we want to pull from the system. And so we pull all these together, the things that the experiment contributes and the software stacks, and we do what's called a unified SPAC building or global build for concretizing. And we do this after, of course, bootstrapping a compiler, which we've already built, and we install that with a lock file on the Jenkins build node. And we found that we need to do this to discover all the transitive dependencies of the experiment root specs that were not built in our software suites, especially Python analysis tools. So we're trying to deliver what we had already been doing, which is pre-building our software stacks and installing them on CVMFS, and then the experiment was supposed to be able to come along and just use that without having to rebuild that. But well, as you know, SPAC likes to rebuild things if you put in new constraints. And so we had the unified environment, so we get all those things, and then we were trying to remove then the experiment root specs because we don't want to build it, we don't want to get in the business of building their software for them and distributing it on CVMFS. We want them to build it, but they do have the expectation that we have already built their dependencies. So I found that if I go and do in the environment and I do a SPAC remove of these root specs, then these transitive dependencies disappear, which it may be by design. And we tried coming up with a script that just goes in and manipulates the JSON in the lock file and just remove the roots directly. But I found that doesn't always keep the transitive dependencies. So the end result is that once we figure out what these transitive dependencies are, we put them back in as root specs themselves. And of course, we have build caches to get our builds from our Jenkins build nodes over to our CVMFS installation server. And well, you probably heard about CVMFS if you attended that session, but it's an interesting file. It's a read-only file system that distributes files over HTTPS. Okay, so once we have this properly trimmed up environment available, we tell the experiment build managers where this path is. They add it to their environment config and using the reuse from type environment. And we also have the parent SPAC installation on CVMFS is included as an upstream because otherwise it kind of confuses the well, I don't know. Otherwise, it tries to build everything again. So there's some examples here of, let's see, this is the one that I created as an example for the Dune experiment, and then there's also the one that they actually used. And then there's an example of their packages. Like, I should be able to click on these, right, Todd, to go to them, or, well, you can look at them later.
Yeah.
So we are finally converging on delivering a common environment that the experiments can reuse without having to rebuild a lot of the packages. And we've onboarded the Dune experiment. We have one particular postdoc working on that, and we are working with a graduate student, I think, from the SVND experiment. And we've heard that Icarus will eventually get back to us when they have someone to work on it. And we're open for suggestions on how to remove the root specs for the experiments without removing their transitive dependencies.
We actually had a request from University of Oregon for something like this, where you basically say you have a root spec that you don't want to build, and then,
Yeah.
or you don't want to install, and then but we still consider it for unification. We still consider it for resolving transitive depths, and we install everything else.
Let's see if this works. Okay, well, this is pretty small, but so this is an example. So we have the environment. We're including things like the toolchain definition and all the experiment packages. Is this, which one is this? This is the Dune release one.
The Git includes how to make that nicer.
Huh?
The Git includes how to make that prettier,
Yeah, well,
and the environment includes that we're going to put in.
I think I want to show you one of the other ones. Unified spec environment is more like the one I wanted to show you.
Yeah, 1.1 does Git includes.
Okay.
No, we don't. We have a request from someone else that
But
we're
you,
planning to do for
you said there was a
1.2.
request not to build certain root
Yeah.
specs, but it would build their dependencies.
It's basically they want particular root specs considered for concretization, but they don't want them installed or built because they know that they have errors. Yeah.
You could do that now, right? Except you have to be explicit of what you're going to install in the environment. So I can install an environment without installing any of the root specs, but I still have an environment that has all of the root specs.
You can't. Yeah. You
Like a nicer interface to do that.
Okay.
yeah.
Instead of having to say like spec install dash dash only dependencies root 1, spec install dash dash only dependencies root 2, spec install root 3, just the way that you can do that is spec install and
Not
root
that.
1 and root 2 aren't being ignored. So like a pen, basically. Right. Yeah, the same
Yeah.
thing as like from the CLI you can do install only dependencies.
You could list like a series of like 8 roots or a way to naturally replace a root with what is installed as new root.
So for development practices, right, sometimes people want to make changes to Larsoft and to their experiment code at the same time. So we actually have to include all of the specs for the experiment code, even if it is a dependency, and especially because it's a dependency, because we've been trying to model the dependencies among our packages so that the proper things get rebuilt if someone changes a low-level package. And just to complete the thought here, we define the root specs by config variables, just for completeness here, and then we add them as root specs here. And I wanted to show one other thing, which was that the experiments, right, so when they specify what packages they want built, well, they also include things that they would really like to have. They want CUDA, and they want TensorFlow built with CUDA, and a couple of other things, but particularly what we found is that when they include things like PyTensorFlow and it gets rebuilt, or they include a Python package as a root spec, that one of the really big packages that you guys have to build, it's the root framework, right? This is what we use for C++ introspection and visualization. That gets rebuilt, and that causes like at least half our stack to get rebuilt. So anytime an experiment adds a Python package for analysis, and if it somehow shifts the Python version, or creates a new Python or installs a new Python, we end up with, they end up with a different stack. And so that was another motivation for trying to gather all of the things that they want in their runtime environment. And the only one I can think for sure is PyTensorFlow. And I think another one I was looking at was, IPyKernel. I was trying to add that the other day. And that ended up causing a difference in Python. Or, well, it was actually pretty free, and it would pick a version. Sometimes it would pick 3.14, sometimes it would pick 3.10. There was a request from some experimenters on Dune to only use Python 3.9, which is the system compiler on ALMA Linux 9, because they have some packages that can't be ported to 3.10 yet. Yeah, we get all sorts of requests from experimenters after we've built and distributed this thing and put it on CVMFS, and then they get upset if we have to change things or remove anything. But anyway, that's it.
Okay,
I could ramble on, but I won't.
that's good. Thanks. All right, any questions for Patrick? No questions? Okay, people already talked to Patrick. All right, the last talk. Phil has agreed to go last, and he will say controversial stuff.
Who's what? Oh, okay, I'm.
You don't have to worry about it. Phil's gonna do it.
Oh, he's going to use his own laptop.
Thank you. So I hear I died. Yeah. It's okay, I've been reincarnated with a quarter zip. Okay, so this is maybe paradoxical, this title, Reasoning with the Concretizer. I have... Sorry. So basically, I've been doing a lot of work recently where I am less familiar with the environment, and I'm using a very different version, older version of SPAC, and I've been basically needing to do a least squares type of fit between two very large environments, from an old case to a new case. And as I've been going through this, I've been asking myself many questions. And these, I think, are all very natural questions that are still hard for people. And I think there's been a lot of reiteration of that in the talks here. So things like, why do I need to force reconcretize when I added this package? There's not a clear way to understand this. What do I need to change to get this to concretize when it's not concretizing? When it actually did concretize, what changed? And then why can't I concretize? That's the proverbial frustration point, right? The error messages, all of these sorts of things. So when we look at kind of the paradigm that we have here, ideally the promise of SPAC is you tell us what you care about, and then we'll figure out the rest, right? And so by definition, with a SPAC.yaml or a raw spec, it's a vastly under-constrained piece of information by nature. And then the SPAC.lock is a fully constrained thing by definition. We're saying this is a fully concrete solution. There aren't any more degrees of freedom. So in between this, there is a huge gap. There are many, many possible solutions, and depending on how under-constrained your SPAC.yaml is and how many pieces of input you have in it, like these gigantic matrix environments, it can be a very, very large space. The space grows. It's an NP hard problem, right? Or NP complete. And the way that we're kind of getting the best out of this, how we're coming to that one value, is
Actually, all the possible solutions except the one that's not done.
yes, yes. So yes, there are many. Right. So, but I guess the thing is how we pick that SPAC.lock. Where does it come from? It is essentially an optimization criteria that is kind of set and coded in the concretizer, right? And it gives us this best value. And it's been set up to try to mimic human intuition, but it's not necessarily tunable. And it does cause sometimes some surprising results for people. And when you get the opportunity to dissect it, its behavior makes sense. But the problem is it's very hard to dissect, to understand. So one of the things I've been playing around with a lot is using the prefer and require as kind of tuning knobs on my concretization. So I can't share with you the source code right now, but hopefully soon, but I'm going to share with you some philosophies. The names themselves are idiomatically like expressive, and you could probably write this in a couple of days with an AI model or something. But one of the ways that I've worked on this is the lock is the fully constrained, but kind of, it's not translatable to running the solve again. It is the solution to the solve. So basically, I've created this tool, lock to YAML. You give it a lock file, and what it does is it scrapes everything out into a new spec.yaml, and all of those things are specified as requirements. It is functionally equivalent, but you can see it, it's editable, you can make changes. And one of the other kind of options that I've added to this, since it's a large graph and things sometimes go wrong, is you can give it a subset of specs that it will add as roots. So you can keep all of the constraint space that you originally have. You get all of the solutions for things that you may be cutting out of the graph but are influencing the solution. And you can just investigate like all the way down to zlib or something like that. Now, yeah, let me run through this and we can take questions. Okay, so then kind of the next step is once you do this, you can then start mapping things that were set to require to prefer. And this is basically saying to the concretizer now, may I change this? What happens when I change this? And you can start to reconcretize in a very constrained state. So if I want to add in something, like I want to see if I can, heaven forbid, change like an option on boost, I can relax a bunch of stuff around boost and see if I can solve. And even still here, it doesn't fully answer the question of what changed. And so that's kind of the next step in my process is this prefer not satisfied. So it's a very simple idea. You run over all of the preferences and you see if they are satisfied by the solution you compute. And you can see then, and the way I have it set up is it dumps out the full spec and then the part that wasn't satisfied and what it picked instead. And from this, I find some very interesting things like, oh, the reason why you're picking this old version is because we have a variant that doesn't exist on the newer version, and I encoded a value on that. Or, hey, if you do this, you actually cut out, you can't use zlib-ng, but that gives you fewer packages, and that's a very high weight in the optimization criteria. So you're giving me an older value that I don't want, but it's because the optimization works out. And I can now nudge it to what I want. So this is a very helpful way, but in order for it to work, you kind of need to get to this highly constrained space and then start backing it off. And the way that we tend to work in SPAC is not that. We start with what we think we want, and then we just kind of pound and pound against it, trying to tune and add things. But the solver is giving us a solution space to start. And then kind of the last piece to the puzzle, and this is the most complicated one, is essentially to be able to rerun the solver. And what this last one does is you dump out the ASP, and then you rerun it, and you can reconstruct every solution that it may give, and then diff them. So I construct the specs, and then I run SPAC diff on them. And so from that, I can see what's going on. And one of the things that I discovered, for instance, I could not figure out why I was still getting like 6 available solutions. I thought I had everything constrained. And the reason why is I hadn't set a requirement on the virtuals. And so the solver would go through and cycle and give me 6 or 7 different virtuals. And that sort of thing is like if you don't have a sharp peak, right, in terms of the optimization criteria, you can nudge and get very surprisingly big results because the virtuals are almost always low in the graph. So this is the sort of thing that like looking at it a little bit differently can give you new intuition into what the concretizer is doing and make it feel a little bit less maddening. So this is what I've been doing, and I hope to kind of productionize it and move it into Core SPAC fairly soon. The takeaways that I think is most important and what I would encourage people to think about is there is a very, very big gap that exists between what you are giving to SPAC and what you're getting out of it. And they are both things that you want, but iterating between them still feels NP hard, right? Like I've heard this over and over again. I think there's a better way. And I think it's basically find a state of truth with the concretizer and then relax from there. And for big problems, make them smaller, but don't relax the constraint space of what you're trying to solve, right? Like if you say, I have 3,000 specs, and now I'm just going to solve one, you have fundamentally changed that problem forever, because all of those other specs are going to influence how that one spec solves. So you have to capture the space that you're trying to solve. And yeah, that's basically it. I would make an analogy to it, like for those of you who have numerical methods backgrounds, like multigrid, this restriction and prolongation type of methodology. You take a very high fidelity problem, you try to restrict it into a smaller problem, but without compromising the original signal. So that's my talk. Take any questions.
Any questions for Phil? Hold on, before I do questions for Phil, do you mind if I put up an image while you're?
Yeah.
Okay. We've actually designed the user interface that you want for SPAC, and I have a picture of it. This is what it will look like.
That's what I would like, yes.
Tom and I send each other this image pretty frequently when we're talking about things.
This is actually different from the one that you sent. This is Conquer.
Have you tried round tripping lock to YAML, YAML to lock to show that it's idempotent, that actually all of your requirements are
Yes.
individually?
That's how I discovered the virtuals, is I found that I could not get a unique solution until I constrained them. So I was able to like show I now have a YAML file that is actually fully constrained, and that was the last piece of the puzzle, is that I kept on getting, when I run SPAC solve, I would see 8 solutions. I could not figure it out. And it wasn't until I wrote this, and I was like, I am pretty sure I have nailed down everything that exists in this graph. And it wasn't until I did that and I actually used the solver itself to tell me what were the available degrees of freedom that I could guarantee that I have an exact solution in YAML form.
Other questions?
So this is great because this is a kind of a more elegant way of debugging a problem that I just ran into on our side about 3 weeks ago, where somebody did something seemingly unrelated in the inputs and in the input specs, and it made a bizarre change that and this is the important part, that nobody caught for weeks, right? That turned off a significant portion of our dependency graph. And so it's great to see this as being thought of in a more systematic way than the very clunky manual debugging that I had to go do to figure it out. Something else we'd like to see, and that's rapidly elevated in priority because we've already seen, I think, 4 instances of it breaking in the last couple months, is a intelligent concretization diff tool. And I say intelligent maybe meaning you can allow certain things to diff between concretizations. We want developers that are working on the environments to be able to understand what changed between concretizations as they went. We're definitely going to write something like that. We don't think it's that complicated, but it might be specific for our use case, what we care about being able to be different. We don't care if the versions of our internal packages change, but we do care if one of them suddenly turns off and we start building GPU-enabled code for one of our TPLs in a CPU-only environment, both of which have happened.
So I will add, Sam, there is a tool I wrote in the SPAC Manager repository.
That's what we will be building it on top of.
Yeah, so it does need some work. It's not perfect. It assumes you don't have duplicate nodes, which Greg has shown is no longer valid in the model. But beyond that, like, the logic is there to do that. You give it 2 lock files.
Any other questions? Okay, we do have a version of it. Oh, yeah, here you go.
I guess one thing that comes up in this is that you kind of get some benefits if you're doing reuse and you've installed a whole environment, and then it is often going to snap back to your existing configuration. But Yeah, no. And so this makes me think like maybe we need to have a weight applied for changing concretizations. If you just do like, okay, now I need to do force, but like don't throw out the whole old solution. Use the previous lock file, construct those as all preference constraints. Oh, okay.
Todd has a PR for this. I've promised to finish it. So I think so he and I talked about this. I think it is good to put this into SPACs like background as the fundamental tools. But the reason why I feel like this talk is important is that there's just a level of understanding that a lot of power users here are still not grasping. And even I've spent like multiple weeks just kind of obsessed over this problem, and it was like virtuals eluded me, right? So I think that by making a format that people can access and do kind of controlled experiments with concretization, it will inform better knowledge, which then could actually lead to better optimization criteria, right?
You want a concretization blast tank? Is that
yeah, kind of. But I mean, like, yeah, the intuition that is there is basically the best guess of Massimiliano, Todd, and Greg, for the most part, and and Peter, and the optimization criteria, right? Like it's good, but it's not always exactly what we want, and there could be different flavors. And I think that the more we democratize this and we find ways to communicate it, it's actually, the concretizer almost always does exactly what it promises you it will do. It's just you don't know what it's promising to do because it's a big, complex space.
Have you seen one of my first slides on the new concretizer? Where if you build, say, the first test that I did with it was to try to build HDF5 caret MPICH and to show that it came up with HDF5 with MPI enabled, because it was just to notice flip the MPI option, right? Mm-hmm. And then I did HDF5 without MPI caret MPICH, and I was like, clearly that'll fail. It didn't.
Yeah.
It found HDF5 with MPI disabled, but with a dependency through CMake to Qt to Valgrind to MPI.
Yeah.
Enabled. So there are, which is why we now have the direct dependency thing in SPAC,
right.
which is much better. Yeah, okay, sorry. Yes.
So I guess this is something I kind of just thought of, but is there an appetite for, I know you mentioned, for example, like having you're getting an old version of some package that you depend on because you had some variant specified that only applied to specific versions. Is there an appetite for package maintainers to have kind of like a cleanup utility that would be available that could help you kind of like lint your packages for like, hey, by the way, like you might want to add this version restriction or something to this particular variant because it looks like, like you may have broken some other packages and SPAC packages with that. It'd be kind of an interesting thing, right? Like, because it seems to me a lot of the issues with concretization come in because like things are slightly out of sync, or you have this like non-ideal behavior because things your packages may be overly complicated for what it actually needs to do.
Yeah.
Do you want to answer that?
You can answer if you have an answer.
Well, I mean, it's a little. I mean, that's like static analysis on the package files themselves, which we're adding like more of. So you may have noticed that we like check whether a version exists when you add a version constraint in SPAC. I found a few places where packages had specs that didn't parse properly, like in .satisfies expressions.
Yeah.
Like there's a lot more we could add there. And the common complaint from earlier today was that people were referring to non-existent variants. And like we could lint that totally. So yes, we can do that.
Yeah, I mean now that you say that, that reminds me, the precursor to this, one of the things I did with trying to span across these spaces was to take the two package repos, compute every Python object in them, and then diff them. And you can see like these are all the variants that disappeared, and these are all the different attributes that changed. And that was actually very insightful. So that also could potentially be a nice tool if it was cleaned up for like evaluating when you want to update your package repo, what kind of things might happen.
So this is maybe more of a question for the group. We have talked at times about adding configurable options to reorder the optimization criteria. And we have not done it because it could be a giant foot gun, and it's fairly difficult to think through what the implications of that would be. I guess I'm curious whether people think they have a use case for it, or whether people think, please don't give my users the ability to do that, they will hurt themselves. I see a couple folks had strong responses to that.
Why did you bring this up, Greg?
Yeah.
That is exactly what caused the odd behavior on our side. And when we went through and realized what it was, we did go and check, and we disagreed with one of the orderings of the concretizer preferences. There is a way around it by enhancing the constraints on your input spec. We didn't love the way that we had to write it, like the syntax that it ended up making us put in our YAML. We can get around it, but in that one specific instance, I really had the thought of, I wish I could make it prefer not to do this. Oh, I'm going to have to remember. It was something to do... I'm not going to be able to remember it off the top of my head.
Is it versions and variants?
There's a decent chance someone might agree with you, and we can change it.
It was externals that needed to have... We didn't register a compiler on our external, and so the prefer compiler disregarded that and turned it off.
That's fixed.
Okay, well, then you're great.
Yeah, that was great.
Yeah. It was exactly that.
So a limited example that might be able to make use of this is the struggles we've had to get the reuse facility to very strongly favor the set of libraries that we have delivered, and to discourage at all the rebuilding of anything unless it is absolutely necessary. So the sort of thing that would seem, perhaps good enough for this use is a flag, a flag when you're doing the concretization that tells it, if the reuse doesn't work and you're going to rebuild something, just fail. And then to try again with a more relaxed reuse if the user decides that no, he really does want to rebuild something and he hasn't messed up something in one of his own recipes that is causing a concretization failure. So having the ability to really strongly stress reusing something in favor of almost anything else might be useful for what we want to do.
I have seen a similar appetite from folks before when they just want to use our binary caches, and because there was one hilarious example, we gave when we were spinning some people up, we gave them an example to go install zlib instead of zlibng, and then it would not use any of our binary caches because they had zlib installed and not zlibng, and we built the rest of the caches on zlibng. And so every once in a while I do want a profile that says I really want to weight things that are in the binary cache heavier than stuff that I have locally installed, because then I can clean up what I have locally installed.
You can't do a priority between them. You can say don't consider the things that are local, but you can't say consider the things in the binary first and then, right? You could have multiple levels of priority for reuse.
Although I feel like there's maybe something else for, so I was talking to Brad. It's not, so right now, if you read the paper from SC22 on how we do the criteria, reusing is basically top priority, and then among the things that can be reused, we weight them by defaults, and then among the things that have to be rebuilt, we weight by defaults. It is probably true that there is a certain level of weirdness for an installed package, or for a package in a cache that you don't want to reuse it. I just don't know how to define weirdness. So, yeah, from the Bay Area.
Yeah. So if I may, I think to Greg's original question, but I think it's very much related to this. I think it's premature to add in changes to the concretizer. I think there's just a lot more people who need to understand it and gain another level of intuition. So that's kind of what I realize what I am proposing is still very complicated, the process that I'm showing. Like, you have to kind of really get invested in your graph to want to do all of that stuff. But the side effect of it is you start to be able to think like the concretizer, and once there are more of us that are once we get beyond the fingers on my hands, right, that can do that, people on this planet, then I think that might be the time to start adding knobs for people to try.
You want the democratizer.
Yes.
Or the democratizer.
The democratizer.
Okay, I think with that, I think we're done. Thanks everyone for coming out, and thanks for sticking around for the discussion.